The year is 1919. The world, still reeling from the aftermath of the Great War, is on the cusp of a monumental scientific breakthrough. Amidst the backdrop of post-war recovery, society is beginning to rebuild and look towards the future. This period of reconstruction is not just physical but intellectual, as the early 20th century witnesses a scientific revolution that promises to change our understanding of the universe. In this era of discovery, Arthur Eddington, a renowned British astronomer, embarks on a daring expedition. His goal is to observe a total solar eclipse, a rare celestial event that offers a unique opportunity to test groundbreaking scientific theories. Eddington's mission is to test a radical new theory proposed by a relatively unknown German physicist named Albert Einstein. This theory, known as general relativity, challenges the very foundations of Newtonian physics that have stood unchallenged for centuries. Einstein's theory of general relativity presents a revolutionary view of gravity. Instead of being a force acting at a distance, gravity is described as a curvature in the fabric of space-time, caused by the presence of massive objects. According to this theory, massive objects like our sun warp the space-time around them. This warping effect causes light to bend as it passes near these massive objects, a phenomenon that can be observed during a solar eclipse. Eddington's observations during the eclipse provide the perfect opportunity to test Einstein's audacious prediction. By carefully measuring the positions of stars near the sun's edge, Eddington aims to detect the subtle bending of light predicted by general relativity. As the moon momentarily obscures the sun's blinding light, Eddington and his team meticulously measure the positions of stars that appear close to the solar limb. This delicate task requires precision and patience as they seek to capture the minute shifts in star positions. To the astonishment of the scientific community, Eddington's measurements reveal that the stars appear slightly shifted from their expected positions. This shift aligns precisely with the predictions made by Einstein's theory, providing the first empirical confirmation of general relativity. This confirmation of gravitational lensing marks a pivotal moment in the history of science. It not only validates Einstein's revolutionary ideas, but also signifies a turning point in our understanding of the universe and the forces that govern it. The success of Eddington's expedition catapults Albert Einstein to global fame, transforming him into a household name. More importantly, it ushers in a new era of astrophysics, where the cosmos itself becomes a vast laboratory for testing the most fundamental laws of nature. This triumph of science over skepticism paves the way for future discoveries that continue to shape our understanding of the universe. One of the most profound implications of Einstein's work, and indeed of all physics, is the realization that the laws of nature are universal. The same forces that govern the motion of planets around the sun also dictate the dance of electrons around an atom. This universality bridges the vast scales of the cosmos, from the tiniest particles to the largest galaxies. This universality is not just a philosophical notion, it's a testable prediction. Scientists have spent decades verifying these principles through meticulous experiments and observations. When we observe distant galaxies, their light having traveled for billions of years across the vastness of space, we are essentially looking back in time, witnessing the universe as it was eons ago. We find that the same spectral lines, the fingerprints of elements, are present. These spectral lines serve as a cosmic Rosetta Stone, allowing us to decode the composition and behavior of distant celestial bodies. This means that the laws governing the interaction of light and matter discovered here on Earth hold true in the farthest reaches of the observable universe. The periodic table of elements is not just a local phenomenon but a universal one. This profound realization underscores a deep connection between us and the cosmos. It suggests that the universe is a coherent whole, governed by the same principles everywhere. We are not merely observers of the cosmos, but active participants in a grand cosmic dance governed by immutable laws. Our quest to understand these laws brings us closer to the very fabric of reality itself. Modern physics, however, yearns for an even deeper understanding. While the standard model of particle physics has been spectacularly successful in explaining the behavior of fundamental particles and forces, it leaves some profound questions unanswered. Enter supersymmetry, or SUSY for short, a theoretical framework that proposes an elegant solution. Susie posits that for every known particle there exists a superpartner particle with slightly different properties. These superpartners, if they exist, could resolve some of the standard model's shortcomings. The idea is captivating in its simplicity. Imagine a universe reflected in a cosmic mirror, where each known particle has a hidden supersymmetric counterpart. This hidden sector of particles interacting with our own could hold the key to understanding some of the universe's deepest mysteries, from the nature of dark matter to the unification of fundamental forces. Despite its theoretical elegance, supersymmetry remains just that, a theory. Decades of experimental searches at powerful particle accelerators like the Large Hadron Collider have yet to yield conclusive evidence for the existence of these elusive superpartners. This lack of direct observation presents a significant challenge. Are the superpartners simply too heavy for us to create in our current experiments, requiring even more powerful colliders? Or is supersymmetry in its current form simply not a true reflection of nature? Despite the challenges, the search continues. The potential rewards are simply too great to ignore. Unlocking the secrets of supersymmetry could revolutionize our understanding of the universe's building blocks and pave the way for a new era of physics beyond the standard model. Strings of a cosmic symphony, unraveling the fabric of reality. As physicists grapple with the mysteries of supersymmetry, another captivating theory has emerged: string theory. This theory has the potential to revolutionize our understanding of the universe at its most fundamental level. String theory proposes that the fundamental constituents of the universe are not point-like particles but rather tiny, vibrating strings of energy. These strings, though incredibly small, hold the key to the universe's deepest secrets. Like the different vibrations of a violin string producing different musical notes, the various vibrational modes of these strings give rise to the different particles and forces we observe in nature. Each mode of vibration corresponds to a different particle, much like each note corresponds to a different sound. This elegant framework offers a potential path towards unifying quantum mechanics, which governs the microscopic world, with general relativity, Einstein's theory of gravity. Such a unification has been the holy grail of theoretical physics for decades. However, string theory comes with its own set of challenges. The mathematics involved is incredibly complex, and the theory itself is still not fully understood. It requires the existence of extra-spatial dimensions, curled up and hidden from our perception. These dimensions are beyond the three spatial dimensions we experience in our everyday lives. While mathematically compelling, these extra dimensions remain elusive to experimental verification. Scientists continue to search for ways to detect these hidden dimensions, hoping to unlock the full potential of string theory. A universe in balance, the delicate dance of critical density. Zooming out from the microscopic realm of strings to the vast cosmic tapestry, we encounter another fundamental concept: critical density. Imagine the universe as a vast expanding balloon. The fate of this expansion, whether it continues forever or eventually slows down and reverses, depends critically on the amount of matter and energy it contains. This critical density represents a delicate balance. Too much matter and energy and the universe's expansion will eventually halt, giving way to a contracting phase leading to a big crunch. Too little, and the expansion continues forever, albeit at an ever-decreasing rate. Determining the actual density of the universe, and thus its ultimate fate, has been a central goal of cosmology for decades. The quickening cosmos, unraveling the mystery of cosmic acceleration. In the late 1990s, observations of distant supernovae, exploding stars that serve as cosmic distance markers, delivered a shocking revelation. The universe's expansion is not slowing down as expected but rather accelerating. This discovery, which earned its discoverers the Nobel Prize in Physics in 2011, threw a wrench into our understanding of cosmic evolution. It implied the existence of a mysterious force, dubbed dark energy, that acts in opposition to gravity, driving the accelerated expansion. Dark energy's grip, the unseen hand shaping our universe. The nature of dark energy remains one of the most profound mysteries in all of science. It constitutes roughly 70% of the total energy density of the universe, yet we have very little understanding of its properties or origin. Some theoretical models suggest that dark energy is a property of the vacuum of space itself, a cosmological constant that Einstein himself once proposed and later discarded. Others propose more exotic explanations such as quintessence, a dynamic energy field that changes over time. Unraveling the secrets of dark energy is one of the most pressing challenges in modern cosmology. It holds the key to understanding not only the fate of the universe but also the fundamental nature of space, time, and gravity itself. A tapestry of cosmic wonders, unifying threads in the grand scheme. From the bending of starlight around the sun to the accelerating expansion of the universe, our exploration of theoretical physics has revealed a cosmos far grander and more mysterious than we could have ever imagined. While questions abound, so too does our sense of wonder. Each new discovery, each theoretical breakthrough, brings us one step closer to unraveling the universe's deepest secrets. The pursuit of these answers is a testament to the power of human curiosity and our unyielding desire to comprehend the cosmos and our place within it.